This video is the first in a series about rate equations. In this video, we're going to talk about rates of reaction and something called the order of a reaction. In the later videos, we'll then go on to rate equations and how we can use these in calculations. Before we do anything new, let's just recap what you should already know. So the rate of reaction is the speed with which the concentration of either a product or a reactant is changing. And at A level, we've started using square brackets to show we mean concentration. The rate is going to be measured in moles per decimetre cubed per second because concentration is measured in moles per decimetre cubed, and then you're doing the change in concentration divided by the change in time, which of course is measured in seconds. And we're using superscripts to allow us to do this all in one line rather than writing it as a fraction. Rates of reaction are going to be governed by collision theory, which you met at GCSE, and this is the idea that in order to react, particles need to collide and they need to have sufficient energy, which we call the activation energy, in order for that collision to be successful. The rate of a reaction can be increased by either adding a catalyst or by altering pressure, temperature, surface area, or crucially, concentration, which is what we're going to focus on today. All of these things can be demonstrated using a Maxwell-Boltzmann distribution, which you would have met during the AS. At GCSE, you encountered the idea that as you increase the concentration of a reactant, you're going to increase the rate of a reaction. So for one of your required practicals, you mixed sodium thiosulfate with hydrochloric acid, and you would have seen a sulfur precipitate forming and a cross disappearing. And you would have been shown that as you double the concentration of the hydrochloric acid, you double the rate of the reaction, and it takes half the amount of time for that cross to disappear. But is this the same for every reactant in every reaction? Well, no. Firstly, if you've got a reactant that is in excess, so we've got too much of it, it doesn't really matter if you increase the concentration because you've already got too much of it. That's not the thing that's slowing the reaction down. So a nice way of thinking about this is if you remember when you did photosynthesis in GCSE biology, you had that idea of limiting factors. And we said that if, say, you've got loads and loads of carbon dioxide and that's not limiting, photosynthesis might be limited by something else like light or temperature. And so it doesn't matter if you increase the concentration of carbon dioxide because it's the other things that are slowing down the reaction. And it's exactly the same idea here. If you've got one reactant in excess, if you increase that excess, it's still just in excess. The reaction isn't going to go any faster. But you also have other reactions where something might not be in excess, but it's still not affecting the rate. And that tends to be where you have multi-step reactions. So at GCSE, we kind of pretend that everything always happens in one go. It's the exact same thing we do with photosynthesis. If you're doing A-level biology, you'll now know that there's a whole bunch of other complicated processes, and it's not really best summed up by that one little equation that you learned at GCSE. Well, we have the same thing in chemistry. You have multiple steps to lots of reactions, and so it might be that the particular reactant you're looking at isn't involved in the slowest step of that reaction, and so it's not actually going to affect rate in the same way. Now, you're not expected to just know this particular reactant is going to affect the rate and this one isn't, but you do need to be able to look at some data and figure out whether that's going to be the case or not. So for any reaction, we can work out something called the order of that reaction. And this is the sum of all the partial orders of all the reactants in that reaction. With me so far? So the order of reaction is basically a way of telling us if I change the concentration of this particular reactant, what does that do to the rate? Is it like we learned at GCSE where I double this and that doubles the rate? Or does it have no effect at all? Or does it have an even bigger effect than that? And that's not something that you can work out by just looking at an equation. It's something that you need to do experiments for. You need to have data for. So by using experiments, I can figure out what the partial order of a reaction is with respect to a particular reactant. Let's call it A. And what that tells me is if I change the concentration of A, what's going to happen to the rate? And as far as we're concerned for A-level, you have 3 options and 3 options only. Technically, we can get fractional orders and maybe even negative orders, but for A-level, this is strictly multiple choice. And it's really important you keep that in mind when you're doing calculations. You're not trying to work anything out from scratch. You're going to go, is it 0? Is it 1? Is it 2? One of them will be right. So it's not as complicated as it seems to start with. So if the partial order of a reaction with respect to reactant A is 0, which is often the case for enzyme catalyzed reactions and is also going to be the case if that reactant isn't part of the slowest step. What that means is if I double the concentration of A, literally nothing happens. It has no effect on the rate at all. I could double it, triple it, nada, nothing happens. Then you've got a partial order of 1, and that's kind of the intuitive, the way you describe things at GCSE. So if I double the concentration, the rate doubles. If I triple the concentration, the rate triples. If I quadruple the concentration, the rate quadruples, right? That's a partial order of 1. Then you've got a partial order of 2, and this is where we've got an exponential relationship, a squared relationship. So if I double the concentration of A, my rate will quadruple. If I triple the concentration of A, my rate will increase by a factor of 9, and if I quadruple the concentration of A, my rate will increase by a factor of 16. Okay, so those are your 3 options, and you can look at a graph or you can look at some data and say, is this partial order 0, partial order 1, or partial order 2? And those are the only options you have to worry about. So sometimes you get some data and have to work out the order or the partial order from that, but sometimes you're also going to encounter graphs. So these are the graphs for a 0 order reaction, a 1st order reaction, and a 2nd order reaction. And you can see from these that the rate is affected in the appropriate way. So for the graph on the left-hand side, as the concentration doubles, nothing happens to the rate. And for the middle one, for the 1st order reaction, as the concentration doubles, so does the rate of reaction. And for the 3rd one, as the concentration doubles, the rate of reaction is going to quadruple. Well, this is all really lovely, but in practical terms, how do we get these data? You can't just be like, oh, this is the rate. You need to actually calculate that somehow. So if I was actually going to try and work out what the order of a reaction was experimentally, I'd need to start by looking at concentration against time. So each one of these graphs is for a reactant, and I can tell that because at the start of the reaction I've got a lot of it, and then at the end I've got far less, right? So it's been used up, its concentration has decreased over the course of the reaction. Now, for the first graph, for the left-hand side, the 0 order graph, I can see that the rate is constant. And I know that the rate is constant because the rate of this graph is the gradient. And I can see here I've got a straight line graph, it's got a constant gradient, and that tells me that the rate isn't changing. So it doesn't matter that the concentration of this reactant, is going down, the rate isn't being affected by it. It doesn't slow down, doesn't speed up, it's just a constant rate. So that tells me that this is a 0 order reaction. And I could either get this data by doing some kind of continuous monitoring method with a colorimeter or something, or I could also do this looking at the same reaction, starting with lots of different concentrations and then working out what the initial rate would be. Now, the next 2 graphs, it's kind of hard to tell the difference between them if you don't have numbers on the graph. But we've got 1st order in the middle and then 2nd order on the right-hand side. And you can see that for both of them, as the concentration decreases, the rate decreases as well, which is kind of more akin to what we'd normally expect. So as the concentration has gone down, there are fewer particles, so the collisions are less frequent, so the rate declines. And so as these reactants are being used up, the rate is going to slow down. So let's say I actually want to work out what the rate is at any given time. I want some quantitative data so that I can calculate whether this reaction is 1st order or 2nd order. If it's 0 order, that's a bit more obvious, so I could probably do it without a calculation, but telling the difference between those last 2 graphs is really, really tricky. So let's say I want to work out the rate. With my straight line graph, I knew that the gradient was the rate. But working out the gradient of a curve is a little bit harder. So the first thing I need to do is draw a tangent. So you should have met at GCSE the idea that a tangent is a straight line that just touches the curve in one place, and we can use it kind of like a surrogate to work out what the gradient of that overall curve is. So say here I've drawn a nice pink line that touches the curve in one place, and I can then use that triangle and I can sort of say, well, here's my change in concentration, and here's my change in time. And if I do concentration divided by time, I'm going to be able to work out the rate. And that's going to be the rate at this particular point here where my line is touching the curve. So where my tangent is touching the curve. If I wanted to work out the rate a bunch of other places, so like up here where the reaction first starts, and then down here as it's finishing, I would need to draw a bunch more tangents. Okay, so I'd have a whole load of tangents drawn on there, and I would work out the gradient for each one. And it's just worth flagging now, just because it's the first time we met it, that this one up here, where we were starting out, that's what we call our initial rate. It's the rate when the reaction very, very first started. So once I've done all that hard work, I've done my experiment, I've plotted my first graph, I've drawn a bunch of tangents, calculated the gradient of each of those tangents. Now I can plot my second graph, which is the more useful one, and this is rate against concentration. So these are the graphs that you really need to know the shapes of. You need to just be able to look at these and go, oh, this is 0 order, this is 1st order, this is 2nd order. But you can see here, say if we have a concentration that's here, and then we have a concentration that's about double, the rate is still exactly the same. Okay, so my concentration doubles, but my rate hasn't changed. That's zero order. If I do the same thing over here, here's my concentration, and then if we sort of approximately double that, we can see that my rate has also, doubled. And then if I were trying to do the same thing over here, it's a little bit trickier, but I could see that as my concentration has doubled, my rate has quadrupled. Obviously, this would be a lot easier if I actually had numbers on these graphs. So all that remains to be said is that once you've deduced the partial orders of each of the reactants for a reaction, then we can find the total order for that reaction by adding the partial orders together. So say if we have a reaction with 3 reactants and we're first order with respect to the first 2 and second order with respect to the third, then the total order for the reaction would be 1 + 1 + 2, so you'd have a 4th order reaction. Hopefully you're now feeling much more confident about partial orders and you're ready to move on to some rate equations. If you did find this useful, then don't forget to like and subscribe for more A-level chemistry content coming soon.